Today, we're going to walk through the VelocityController PID Tuning tool in the Fidget Control panel for Windows. This tool can help you experimentally determine the best control parameters for your motor or assembly. Open the Fidget Control panel and double-click the VelocityController channel. Switch to the Tuning tab to access the PID tuner. Before we begin, we need to start by filling in some of the configurations. Click on Defaults to load the default control parameters. These are the values we'll be adjusting in our test. If you have an encoder for position feedback, remember to check the Use Encoder box. If the box is unchecked and you're using a brushless motor, the control loop will use the motor's Hall effect sensors. In most cases, an encoder will have much higher resolution, resulting in smoother control. If you're using a brushed DC motor, this checkbox won't be present since an encoder is your only option. Next, set the rescale factor for your motor. This will cause all other values to be converted into more easily understood units like degrees or rotations. Check the user guide for your motor controller to learn how to calculate your motor's rescale factor. We'll enter a value that rescales everything for the system into degrees. Our acceleration is now in degrees per second squared. We'll set our acceleration to 3600, which means the controller will reach a target velocity of 1 rotation per second in 1/10 of a second. We recommend setting your current limit to 1.1 times the rated current of your motor. This motor is rated for 7 amps, so we'll set the limit to 7.7. We'll ignore the surge current limit for this video, but you can read more about it in the VelocityController API guide. Now set the interval. This is the time in seconds the motor will have to try and reach the target velocity, and the time it will have to slow back down to 0. We'll set it to 3 seconds, so each test will be a total of 6 seconds long. The step size sets the velocity our motor will attempt to reach. We'll set it to 360, which is 1 rotation per second because of the rescale value we set earlier. You'll notice that each setting is green or red. Red means that the value has been changed but hasn't been sent to the controller yet. You can send it to the controller by pressing Enter or by engaging the motor or starting a test. I'll enter some safe tuning values to start with so we can run a test and see the graphs. Click Test. You can see the motor spins, stops, and 3 graphs have appeared. The first graph shows the motor velocity over time. The green line is the target velocity. This marks the velocity you've selected for the test. The purple line is the expected velocity. This is the calculated target for the PID loop, based on the acceleration and step size you've chosen. The red line is the actual velocity of the motor according to the encoder or Hall effect sensors. This is the line that will respond to changes as we tune the parameters, and our goal will be to get this line to follow the purple line as closely as possible without causing other problems for our motor. The second graph shows the error in the control loop. Error is defined as the difference between the current velocity and the expected velocity. The third graph is the duty cycle graph, which shows how much power the controller is giving to the motor. 1.0 is full power, 0 is no power, and -1.0 is full reverse. Together with the error graph, it can provide insight into what the position controller is trying to do. As you do more test runs, your previous 2 tests will be overlaid in different colors, so you can see what difference your last change made. If we zero out Ki and Kd and set Kp to 0.01, this means that as long as the motor is 100 or more degrees per second away from its target velocity, it will turn at full power. Likewise, if error is at 50 degrees per second, it would turn at half power, and so on. This gives the controller the ability to maintain velocity even if external resistance is applied. While Kp is the primary contributor in a position control loop, it has a much smaller role in a velocity control loop. This is because velocity control is all about reaching and maintaining a speed over time. Kp only reacts based on the error it sees in a single moment in time, which can easily lead to instability. If we set a Kp of 0.005, you can see the motor vibrates violently as it spins. It's been given too much strength, so it gets stuck in a cycle of rapidly overshooting the target velocity and then overcorrecting. Let's lower it to 0.001 and try again. You may have noticed that the motor falls about 100 degrees per second short of our target velocity. This is expected because a Kp of 0.001 means that an error of 120 degrees per second results in 0.12 duty cycle, and you can see that reflected in the error and duty cycle graphs. If we keep adding Kp, we'll get closer to the target, but we'll get vibrations again if we try to get there with Kp alone. In order to hit our target, we'll need to add some Ki. KI looks at the error over time and pushes the motor harder the longer the error persists. This makes it well suited to being the primary parameter in a velocity control loop. For example, KI of 0.01 would push the motor to full power when the error is 100 degrees for 1 second. Similarly, it would contribute 0.5 duty cycle if the error was 50 degrees for 1 second, or 100 degrees for half a second. With a KI of 0.01, the motor now reaches our target of 1 rotation per second. If you raise KI too high, the motor will vibrate as it rotates, just like it did when KP was too strong. KD is different because it works against KP and KI, dampening the drive towards the target. This can be used to reduce overshoot. Because this position controller uses a trapezoidal control algorithm, KD is not as effective as in classical PID control. Adding too much can cause the motor to vibrate in place loudly, so if you decide to add KD, you should start several decimal places lower than your KP and work your way up slowly. If your system has overshoot, you may find that lowering KP gives better results than adding any KD at all. So continue to use the tool and make adjustments until you're happy with the motor's response. One final parameter to discuss is the deadband. You may find that the motor jitters when holding position at 0 velocity. Let's add a half a degree per second of deadband to fix this problem. Adding deadband creates a buffer zone when the motor is at 0 velocity. This means the controller will be allowed to freely spin as long as it's moving slower than the deadband value. Once you're finished tuning, you can click Save to save the parameters to a file that can be loaded next time. This concludes the walkthrough of the Fidget Control Panel PID Tuner. For more information, see the VelocityController API Guide and the Quick Start Guide for your controller, both of which can be found on the product page for your Fidget.